So this one, I think we're all set. 1 second. So let's start. Acha, we're going to start with this one. This one is summer 19 question paper 2-3. TK, we're going to try and do this one, and we're going to start with the organic question. TK, I'm going to solve this in reverse. So starting with the first question, what he's saying is that there are 3 alkenes, and they have the same molecular formula. So the same molecular formula. So they're basically isomers of each other. So 3 alkenes, which are isomers, whether they are stereo or structural isomers, we don't know, but they have the same molecular formula. Describe what is seen when aqueous bromine is added. So when alkenes, that's an addition reaction, bromination. So the red, brown, or orange bromine gets decolorized. It's decolorized because you have an addition reaction. Whenever you have a double bond, an alkene, the bromines are going to get added to this double bond over here. Moving to the next part, X, Y, and Z are reacted separately with hot concentrated acidified magnate 7 ions until there is no further reaction. The carbon containing products are shown in the table. So hot concentrated acidified magnate 7 ions. So this thing is strong oxidation. So you've got strong oxidation that is happening. And I'll just quickly go through what happens when strong oxidation happens. Let me just open the chart. So what goes on when you have strong oxidation? There are 3 different, just 1 second. So there are 3 different scenarios. You've got a double bond, and the double bond is going to completely break. Okay, let me just show this to you. So over here at the top, and just 1 second. So over here at the top, when you have strong oxidation, the double bond is going to completely break. And if the double bonded carbon atom has 2 hydrogens, it's going to turn into a carbon dioxide and water molecule. If it's got 1 carbon chain, it changes into a carboxylic acid. And if it's got 2 carbon chains, it's going to turn into a ketone. So you've got 3 different scenarios. And let's move back to the question. So what is the question stating? The question states that when the first alkene X, it underwent strong oxidation. So it ended up forming these 2 products, carbon dioxide and water. So I'm going to draw X now. So remember, what is X? X is, it is an alkene. And what type of alkene is it? It's forming a carbon dioxide molecule. So when does strong oxidation lead to a carbon dioxide? Because the carbon, double bonded carbon, would have 2 hydrogens attached to it. So one of the carbons is going to have 2 hydrogens that are going to be attached to it. And that is why when the strong oxidation happened, this thing will break off and it will form a carbon dioxide molecule, which is given over here. Okay, so that's the first part. What is happening to the other part? The other part is turning into a ketone. I mean, this molecule over here, if you look at this molecule is a ketone. Because it's got a CO, C double bond O, and it's got 2 CH3 groups attached to it. So this other molecule is a ketone. So when you get a ketone in this scenario, that the double bonded carbon atom has 2 carbon chains attached to it, and it turns into a ketone. So we're going to do that. So this other double bonded carbon atom has 2 carbon chains attached to it. That's why it's going to turn into a ketone. And what are those 2 carbon chains? The 2 carbon chains are CH3 groups. So it's got a CH3 group on one side, it's got a CH3 group on the other side. So this thing will break off and it is going to form this particular ketone. Okay, is this clear? The first molecule, sign clear?
Yes, sir.
Yes, sir.
So that's the first one. So let's move to the next one. The next one is again, it's Y. We're talking about Y here. Okay, let me rub this off. So the next one is Y. So we've got Y. Again, it's an alkene. It gets strong. There's strong oxidation, carbon dioxide in this molecule is being produced. So there's going to be an alkene. And if a carbon dioxide molecule is getting produced, so that means the carbon would be bonded to two H's. So when it breaks off, it ends up producing a carbon dioxide. And the other part is turning into a carboxylic acid. So when does it form a carboxylic acid? It forms a carboxylic acid when the double bonded carbon atom has one H, and on the other side there's a carbon chain. So this other thing is turning into this carboxylic acid. I mean, this thing is turning into a carbon dioxide molecule, and the other one is turning into a carboxylic acid. So one side is going to be an H, and the other side will have all the carbon atoms. So that's 1, 2, 3. So you got 1, 2, and 3 carbon atoms. So CH3, CH2, and this carbon will turn into a carboxylic acid. So that's the second one. And let's move to part Z. Part Z only produces one molecule. So, and that's a carboxylic acid. So when you get a carboxylic acid, the double bond is going to get oxidized. When you get a carboxylic acid, this scenario, that one of the carbons will have an H, the other one would have the carbon chain. So you'll have an H, and it's forming ethanoic acid. So the other part will have CH3 group attached to it. So when this molecule breaks off, it forms this carboxylic acid. And since you're only getting carboxylic acid, that means the other part is also identical. It's also going to give you the same thing. So it's going to have an H, and it's going to have a CH3 group. So that is also going to turn into a carboxylic acid. So this question is interesting because everything is being done in reverse. You have to know, I mean, you're used to these type of questions that you've got a double bonded carbon atom and it turns into ketone or carboxylic acid or carbon dioxide. This is the same thing done in exactly the reverse. Okay? So is this question clear?
Yes, sir.
Okay. So next one, reduce the molecular formula of X, Y, and Z so we can, I mean, all of them are isomers of each other. So that's 4 carbon atoms and 8, I mean, you can count them. It's 4 carbon atoms and 8 hydrogen atoms. The structures of B and W are shown. What is B and W? I think it's not linked to this. So it's a completely different question. So name the class of compounds that B and W belong to. So they're obviously alcohols. Both of them are alcohols, but what type of alcohol is this one? And what type of alcohol is this one?
V is primary alcohol. And
Okay,
W is alcohol.
Okay, so V is primary alcohol. And the other one is your tertiary alcohol. Because this carbon atom, the one with the OH over here is bonded to 3 carbon chains. The one over here, the carbon with the OH, that is bonded to 2 hydrogens and only 1 carbon chain. So that's the primary. Both react with sodium metal. Write an equation for the reactions of V. V is this one. So what happens when they react with sodium metal? This is 2 and CH2 and OH. So what happens is that the alcohol H gets displaced. So you get CH2, 2, CH2, and O minus 1 and Na plus 1. Plus hydrogen gas is going to be produced. So remember this. 2 things react with sodium metals. One of them is an alcohol. That alcohols, they react with sodium metal. And the OH changes into O minus 1 and Na plus 1. And the other one is carboxylic acids. Carboxylic acids not only react with sodium metal, they also react with sodium hydroxide, which is a base, sodium carbonate as well, and ammonia as well. So in all cases, they end up forming a salt. And depending on with the metal, they're going to produce hydrogen. With base, it's going to produce water, and the other one is going to produce carbon dioxide as well. But alcohols are weakly acidic. Alcohols are like terrible acids. The only acid type reaction that they undergo is this one. They react with very reactive group 1 metals. So moving on, next one. We've got name a reagent used to distinguish V and W. Describe any observation. How would you distinguish a primary alcohol with a tertiary alcohol?
Try iodine.
Firstly, that will not happen because for triiodomethane, you need a methyl group with COH and H in the rest of the molecule. You don't have that structure in any one of them. Either the CH3 is not with the OH over here, the CH3 is not with CHOH. It has to be CHOH. So in both cases, the triiodomethane reaction, I mean, this one is not going to, it's not going to work. This one. Okay, the iodoform test is not going to work. How do you, it's a very simple question. How do you distinguish a primary with a tertiary alcohol?
Simple oxidation with
Sir,
K2Cr2.
SN1.
No, simple oxidation. No, simple oxidation. Like it's a primary alcohol gets oxidized. Okay, primary alcohol gets oxidized to an aldehyde, and the aldehyde further gets oxidized to a carboxylic acid. A secondary alcohol gets oxidized to a ketone. Tertiary alcohols have no oxidation. So you can write just K2Cr2O7. The primary alcohol will get oxidized. So the reagent would be, so what are the reagents? It's going to be acidified. K2Cr2O7. And they're not looking for the conditions, but the conditions are heat with reflux. You're going to heat it. So one of them is going to get oxidized, the primary one. So the primary alcohol will get oxidized, so V will get oxidized. So what is the color change that's going to happen? It's going to be orange to green. Okay, you have to remember that K2Cr2O7 has this color change. And the other one, tertiary alcohol, no reaction for that one. Okay, so that one is not going to have any reaction. And you must know all of these. KMNO4 is going to be purple to colorless. If you could have used KMNO4 as well. These were the only two options for alcohols. For aldehydes, you've got other options as well. Apart from K2Cr2O7 or KMNO4, you could also use Tollens or Felling. Actually, moving to the next one. The last one, okay, we're done with the last one. Let's move to the previous question, which is this one, that sample of this looks like an organic reaction as well. It's about halogenoalkanes they react with a number of different reactions in nucleophilic substitution reactions. A sample of potassium cyanide dissolved in ethanol is added to a sample of 1-bromobutane and heated under reflux. A nucleophilic substitution reaction occurs and compound A is formed, and you have to name compound A. So first thing is that what is the reaction? It's substitution. Halogenoalkanes, they undergo substitution reactions with which? With CN and with also with NH3. So the halogen is going to be displaced by CN -1. So your molecule will now be, instead of Br, I say it's CH3, 3 times there is CH2. TK, I'm talking about this molecule over here. As there's another CH2, and then there is Br. So what is going to happen is the Br is going to get replaced by CN. There's going to be a substitution reaction that's going to happen. And what is the name of this molecule? It's a 1, 2, 3, 4, 5. So what is the name for this one? Yeah, anyone? What's the name? Saim, कोई idea?
Propane nitrile.
The prop is for 3 carbon atoms.
Oh, sorry.
Sir,
Pentane.
butane nitrile.
No, pent 5, it's 5 carbon atoms. Okay, always remember that adding a CN, okay, if you add a CN, the number of carbon atoms they increase. So now it's pentane nitrile. Okay, so adding CN increases the number of carbon atoms. So it's now 5 carbon atoms instead of butane. It's going to be propane. So now moving to the next one. What is meant by the term nucleophile? What's a nucleophile? What does it do? What is it attracted to? First thing.
Electron donor.
But what is it attracted to?
So positive charge.
Okay, so it's attracted to, it's a species that is attracted to positive charge, or फिर वो बाकी the other statement that is also correct, which is, and it donates a pair of electrons. ठीक है, or it's an electron pair donor. That's it. Identify the nucleophile in this reaction. So what is the nucleophile? That is Cn-1. Okay, I'll go through the mechanism as well. You got two this one is a primary halogenoalkane. So you got two types of Sn mechanisms. One is Sn1, the other one is Sn2. So we have a primary, we have a bromine instead of his Cl, and Cn-1. The Cn-1 lone pairs are going to get attracted to the carbon positive, and the Cl is going to get knocked out. Okay, so the electrons from Cn-1 are going to come in, and the bromine is going to get knocked out. So that's the Sn2 mechanism, which is going to happen for a primary halogenoalkane. Explain why this reaction is described as a substitution reaction. I mean, that's very basic. A Br atom is displaced by Cn. Hence the word substitution. State the reagents and conditions needed for to convert this thing into amine. So that is also a nucleophilic substitution reaction. That's this one. You either add ammonia ethanolic and reflux, or you're going to add ammonia gas plus heat in a sealed tube under high pressure. So those are the two reagents that you're going to use. So ammonia is going to be ethanolic, and that will have the same, ammonia also has lone pair, so it's going to have the same exact mechanism plus reflux, or ammonia gas in a sealed tube under high pressures. So next one is describe and explain the trend in the reactivity of the different halogenoalkanes shown in this experiment. By looking at the time that is needed, which one is the most reactive one?
Iodine 1.
Okay, and you have to explain that as well. I mean, that's obvious. This is fast. It just takes 40 seconds for the reaction to happen, and this one is slow. So the trend is that that iodine is the fastest compared to the bromine halogenoalkane, and that's even faster compared to the Cl1. So this is the fastest. So what's the reason for that? Well, let's go clearly लिख लो, okay, this is the fastest. So what's the I mean, you have to be described, and now we have to explain.
Iodine bond energy is less.
Okay, it's easy to break the bond. So bond energy is less, or you can say that this one has a weaker bond, or bond energy is less, and this one has a stronger bond. So it's a lot harder to actually break that bond. So you got a stronger bond. Now, all three halogenoalkanes tend to react via the Sn1 mechanism. Explain why the Sn1 mechanism is favored. Now, this one is a tertiary. All of the three are basically tertiary halogenoalkanes. So what is the explanation why tertiary halogenoalkanes? A tertiary halogenoalkane has 3 carbon chains on the alpha carbon atom. And the Sn1 mechanism is this one, where the Br breaks off first. Okay, so it's the Br, in this case it's Cl. The Br will break off first. It will form a carbocation, and then the nucleophile would join in. And I'm going to do this. I'm going to draw the mechanism. Like the Br is going to break off first. So what's the explanation for this?
More alkyl inductive effect.
Okay, and then reaction wo kaun sa raha tha? This was I think it was with water. It's so let's say the OH minus 1 is the nucleophile. Anyways, so okay, that's alkyl chain, and it's a 3-mark question. So So remember this, you got two mechanisms. Either the nucleophile is going to attack the carbon directly, or the Cl will break off first and then the nucleophile would come in. So tertiary halogenoalkanes, tertiary carbocations are easier to form. And the reason is that you got more alkyl chains. Like alkyl chains are electron donating. So what happens is that the carbocation is surrounded by large groups. So the positive charge kind of gets neutralized and which stabilizes the carbocation. So it's a lot easier to form the carbocation. Because if the positive charge is very strong, it would be very hard for the negative Cl to break off. For the Cl to sort of to pull the Cl away or to break off the Cl, you need the attraction to be less. You want the positive charge over here to be very small. And it is small when you've got large groups around it. So that's the reason why Cl-1 can easily leave this carbon, because the positive charge is kind of small. So the answer that you're going to write is that you're going to write that a 3-degree carbocation firstly is more stable. It's easier to form it. Why? Due to more alkyl chains, due to more electron donating alkyl chains. Okay, answers ko na, make sure you write your answers properly and explain them properly. Okay, due to more electron donating alkyl chains. Okay, which is also known as the positive inductive effect, if you want to write that. And that's about it. You don't have to go into further detail. You can also write about which decrease the charge density on the carbocation. So the positive charge becomes smaller and the Br-1 can easily leave the carbocation. So identify a halogenoalkane which tends to react with the aqueous solution of silver nitrate via Sn2 mechanism. So that must be a primary halogenoalkane. So not really sure, it could be any formula over here, any primary halogenoalkane. So let's talk about this one. So this is bromopropane, or 1-bromopropane to be specific. Okay, so that's this one. Let's move to the previous question, which is question number. So let's talk about question number 6 now. So this will explain why high levels of SO2 may be found in the atmosphere near power stations. What could be the reason for that? Where do you get SO2 in the atmosphere? And what's the link between power stations and SO2? Well, it's a very simple question. It's an O-levels question. What do you write for this?
Sir, because of the burning of fossil fuels that release it into the atmosphere.
Okay, first thing, I mean, there are 2 marks. Okay, first thing is fossil fuels, especially the raw ones. Okay, power, you're not using refined petrol for power stations. You're just using really unrefined fossil fuels like coal or furnace oil. So fossil fuels are contaminated by sulfur, or they contain sulfur. And when burnt, that's the answer. When they burn. So that is when sulfur, and you should always write an equation. So when they burn, SO2 is produced. As the next one, during 1 year, 1590 tons of SO2 was released into the atmosphere by a fossil fuel burning power station. Use the equations to calculate how many tons of H2SO4 were formed in the atmosphere, assuming that all of the SO2 release was converted into H2SO4. So 1590 tons of SO2 was released into the atmosphere. So this is 1590 tons. As I use the equations, how many tons of H2SO4 were formed? So the best thing is, instead of converting tons to grams, we can think of this as grams and we can do all our calculations. So we're going to figure out the moles. We're going to figure out the moles of, so I say if you, I mean, since there would be marks for working, how much is a ton in grams? Like, what do I, if I want to convert tons to grams, because moles is in grams, what do I multiply this by?
1 million.
It's 10 per 6. So it's 1590. So just for the sake of working, to show proper working, I think you should do the conversion, because they do give marks for, although you don't have to convert it, you can just write 1590 and do all the working. And that's going to be divided by the MR of SO2, which is, and remember, the MR has to be taken as the exact one. Remember, sulfur is not 32. Don't use your memory. Sulfur is actually 32.1 in the periodic table. So use 32.1 plus 16 into that's 64.1. So what do you get for that? That is how much? Does anyone have a calculator for this?
24.8 into 10 raised to power 6.
That's into 10 per 6 moles. Now H2SO4 will have exactly the same moles. They're going to have exactly the same moles, because one SO2 produces one SO3 and then one SO3 produces one H2. So everything is 1:1. So you don't have to, I mean, it's simple ratios are 1:1. So the moles of SO3 are exactly the same, and that's 24.8 times 10 per 6. And to find the mass, you would multiply it by the MR of this thing. So what is the MR? That's 98.1. I think we check. It's not. I don't think it's 98.1. Sorry, this is not SO3. This is actually we're talking about H2SO4. Take the moles of H2SO4. H2SO4 is 98.1. So you multiply it by the MR and you'll get the mass. So what is the final answer?
2.432 into 10 raised to power 9 grams.
2.4?
32.
You have to convert that into tons. So you're going to divide by 1 million. Which is how many tons?
$2,432.8.
Okay, so it's going to be 2,433 tons. I said, describe how NO2 is also produced in this by these power stations. So what is the process of? I mean, you're burning fossil fuels. Fossil fuels don't have NO2. So how is NO2 getting produced?
Nitrogen and oxygen from the atmosphere. Nitrogen triple bond will be big.
Okay, so nitrogen and oxygen react. Okay, from air. High temperatures provide the activation energy. So they provide the necessary energy needed to break the N triple bond N. Let's just state one natural cause of NO2 being formed in the atmosphere. What's the natural cause of NO2 getting formed?
Lightning.
Okay, so that's lightning strikes. What's the man-made? That's combustion. Okay, cars, car engines, etc. So lightning strikes, air heats up and it burns. Explain why NO2 can be described as a catalyst in the oxidation of atmospheric SO2. So what's the reason for it behaving as a catalyst in this reaction? How can you show that it's a catalyst? What does a catalyst do? First thing, I mean, first thing is it remains unchanged. You had NO2 and he's saying it behaves. Now the complete reaction for this is that the NO2 gets, there's a step that's missing, which is that NO formed is regenerated in the air. The NO forms quickly once it's formed. Once this NO is formed, it quickly reacts with oxygen in the air and it ends up forming NO2 back again. So first thing is it is regenerated and it lowers the activation. That's what a catalyst does. So you don't have to, I mean, details about the working of a catalyst is not part of your course. So you don't have to explain how it's behaving as a catalyst. All you have to tell them is how can you define it as a catalyst, because it lowers activation energy and it speeds up the reaction. Okay. In your course, remember in A2, you have to give the whole description about the method, how does a catalyst work. In AS, you don't need to do that. You just need to know the basic stuff. What does a catalyst do? It lowers activation. What happens after that? The reaction speeds up. And what happens to the catalyst? The catalyst is regenerated or reforms or regenerated. And you just need to know two words. One is homogeneous and the other one is heterogeneous catalyst, which is that homogeneous catalysts have the same phase, same state, and heterogeneous have opposite states compared to the reactants. So moving to the previous question, question number 3, you've got magnesium and one second. As a magnesium reacts with oxygen to form, it's forming magnesium oxide. So state 2 observations that would be made during when magnesium is heated strongly and placed in a gas jar of pure oxygen. So 2 observations. So magnesium is placed, what would you observe when it is heated strongly and placed in a gas jar full of oxygen?
White solid and white bright flame.
Okay, so first thing is it's going to form a white solid. Okay, the other thing is about inorganic, that the flame of magnesium is going to be white in color. So I just quickly open the inorganic notes. Okay, so this is all that you have to. Just one second, where's the okay, so the flame test, I have to remember it's a white flame. Acid indigestion is caused by an excess of hydrochloric acid in the stomach. Magnesium oxide is commonly found in indigestion tablets. Give the equation to show magnesium oxide. How does it relieve indigestion? So, and he's talking about hydrochloric acid. So magnesium oxide is a base. So you just have to write an equation that it reacts with HCl, ends up forming a salt, which is magnesium chloride, plus water is going to be produced. So the acid is going to get neutralized. Name the type of reaction that's an acid-base reaction or a neutralization reaction. Magnesium oxide is described as a ceramic material. It has a high melting point. State and explain why ceramic materials such as especially magnesium oxide have very high. Now they're firstly, ceramic, remember, is a material that has a certain property. What are those properties? They've got very high melting points and they are structurally, they're very strong. And they're non-conductors. So any substance, even sand, is basically a ceramic material, because clay or sand, because it has a very high melting point, you make ovens out of it. Structurally, it's strong. I mean, clay is kind of strong. You can make a house out of it. And it's a non-conductor. So going to this, why is magnesium oxide so strong? What's the reason behind that? Okay, let me see if I can find it here. Now, it's not given. I think it's not given away. But I'll just quickly tell you. As a first thing, for magnesium oxide, can anyone tell me what type of compound is this? Covalent or ionic?
Giant ionic.
Okay, so first thing, it's got a giant ionic lattice. Now, a lot of compounds have giant ionic lattices, but but they're not strong like table salt. That's a giant ionic lattice, but it's not very strong. Why is magnesium oxide, which is a giant ionic lattice, why is that so strong? Like if it's an ionic lattice, what is the reason of its extra strength? Okay, what is the charge on the ion?
There's strong
What is the
intermolecular
charge?
force.
The intermolecular forces are for covalent compounds. Okay. So magnesium oxide has two ions. One is Mg+2, the other one is -2. So you got a -2 alternatingly they're arranged. So remember this, whenever you have an ionic compound, not all ionic compounds are strong. I mean, they are kind of strong, relatively speaking, compared to other compounds. Even table salt is kind of strong. But the ionic lattice, the extra strength of magnesium oxide comes because of the stronger attraction. Like every particle Mg is +2 and O is -2. So because of the greater charge and the smaller ion, so greater charge density. So the greater charge density of the ion of ions, both ions are very small. So that means the ionic lattice is going to be very tightly packed. And because of the charge is greater, +2 and -2, the attraction is going to be a lot stronger as well. So due to greater charge density of the ion, there is stronger ionic attraction or stronger ionic bonds. So more energy is needed to break the lattice. Hence, they have very high melting points. So remember this, okay, ionic compounds are strong, but some of them like aluminum oxide and magnesium oxide are very, very strong. And the reason for the extra strength is because they're smaller in size and the charge is greater. So the attraction between the ions is a lot stronger. And the same question would also come about silicon dioxide that silicon dioxide is also a ceramic material. But in that case, the explanation is different because silicon dioxide, where's silicon dioxide? So in that case, you're going to talk about silicon dioxide having a giant covalent structure. Where Si is bonded to oxygens and oxygen is bonded to silicon. And there's a large network of very strong bonds, covalent bonds in that case. Okay? So that's the reasoning behind that. As I write an equation for this reaction, magnesium oxide can be made from magnesium carbonate. So that is decomposition. And name the type, that's decomposition. So that's it. Okay. So remember, most of you lose a lot of marks on basic questions. Like people don't, I mean, they know what the answer is, but they don't know how to properly write those answers. So moving to the second question. At room temperature, iodine is a solid. Okay, so we've got iodine, which is describe the arrangement of the iodine molecules within the solid. So what type of arrangement? It's a covalent molecule. How are covalent molecules arranged? Okay, how do you describe the arrangement?
Closely packed.
Okay, so and he's talking about specifically within the solid. So it's going to be a regular arrangement and they're going to be tightly packed or closely packed. Okay, and you have to focus on because there could have been a number of answers for this. Okay, it's a simple molecular lattice, but over here they're not even talking about the type of bonding or etc. They just want to know how are the particles arranged within the solid. As I list all of the forces of attraction between solid iodine and identify which of these are overcome in solid iodine. So iodine is like this. It's a covalent, it's a diatomic molecule with covalent bonds. The next one is also going to be a diatomic molecule. So all iodine molecules will be covalently bonded. And there's going to be strong intermolecular forces that would exist between the particles. What are those intermolecular forces in the case of iodine?
Permanent dipole.
It's not going to have permanent dipoles. It's going to have It's a non-polar molecule क्योंकि दोनों iodine है ना, so both of them are iodine. So the dipoles will cancel out. So it's not going to have a dipole. So first thing, they have covalent bonds. That's the first type. That is between the atoms. And there's going to be weak van der Waals forces. Between molecules. So you're going to have weak van der Waals forces between molecules. And which force is broken when it vaporizes? The covalent bonds or the weak van der Waals forces?
Van der Waals forces.
Okay, so you break the weak van der Waals forces. That's the answer to this part. So anyways, this is the dimerization of AlCl3, which over here they're using iodine. How many coordinate bonds are made when a molecule of Al2I6 is formed from its atoms?
2.
So 2. Do you remember that you've got aluminium making 3 normal bonds, and there's another aluminium that's making 3. Cl के साथ भी यही होता है. With Cl you get the same thing. The iodine has lone pairs. Aluminium's outer shell is not complete, so they end up forming a dative bond. This iodine also has a lone pair, and the aluminium goes and bonds with them. Describe how coordinate bonds form within this molecule. So you just have to describe that the lone pairs from iodine, they donate a pair of electrons to the aluminium atom, forming a dative covalent bond. That would be a 1-mark explanation for that. In the reaction between hydrogen iodide and concentrated sulfuric acid, the products are hydrogen sulfide, sulfur, iodine, and water. You may wish to use oxidation numbers to help you write an equation. So the reaction is between Hi and sulfuric acid. Hydrogen sulfide is produced and sulfur is produced, and water. Iodine is produced and water is produced, right? Now you got to balance this equation, and this one is probably a pretty tough equation to balance. Like remember, when you balance the redox equation, you need to balance the number of electrons that are gained and that are lost. So यहाँ पे we're going to do the same thing, because you can't balance the redox equation until and unless you've balanced the number of electrons that are being gained or lost. So starting with sulfur is +6. I mean, you can find the oxidation state of sulfur. I think it is +6. Oxygen is -2. Hydrogen is +1. So this comes out to be +6. You can double check that. Sulfur over here is -2, because hydrogen is +1 and sulfur over here is 0. So what is happening is sulfur is getting reduced. And now to reduce this, firstly, I'll just balance sulfurs, because there are 2 sulfurs on this side. So I'll just make 2 sulfuric acid. So let's say 1 sulfur goes from +6 to -2. So that's a gain of how many electrons? 8 electrons. Right? Sulfur goes from +6 to -2. So that's a gain of 8 electrons. Sulfur also goes from +6 to 0. And that is a gain of 6 electrons. So that is reduction. So basically you're having reduction. And in total, how many electrons are being gained? 8 electrons gained when you want to make H2S and 6 electrons gained when you want to make sulfur. So that's a total of 14 electrons, right? So 8 plus 6 electrons, that's the amount of electrons that are being gained. So whoever is getting oxidized, it must lose the same number of electrons. So who's getting oxidized? The element that is getting oxidized is iodine. It goes from -1 to 0. So it goes from all the way to this point. So 1 iodine loses how many electrons? -1 to 0. So that is a loss of 1 electron, right? So we wanted to lose how many electrons? We wanted to lose 14 electrons. So if I want to make it lose 14 electrons, I would have to multiply it by 14. So there's going to be 14 iodines, so 14 HIs, and 7 I2 over here because that's a diatomic, so that is 14 iodine. So now the number of electrons that are gained and the number of electrons that are lost have now become, I think they have now become equal. Sulfur gained electrons, 8 over here, 6 over here. That's a total gain of 14 electrons. So somebody is losing 14 electrons, and that somebody is iodine because -1 to 0. So it lost 1 electron, so it should lose 14 electrons. So I multiplied it by 14. And I've done that. Now the only thing that's left to balance is the water. So I'll just look at the oxygens. That's 8 oxygens over here. So I guess there's going to be 8 water molecules. And that would be my balanced equation. Is this clear?
Yes.
Okay, just remember how to balance redox equations. You can't balance them using the normal method. You have to balance the number of electrons that are being gained and lost. I said, next one, explain with reference to oxidation number why this reaction is a redox reaction. So we just already did that. Tell them that HI goes from -1, or iodine goes from -1 to 0, and sulfur goes from +6 to -2, and also goes from +6 to 0. So that is reduction. So they're gaining electrons, that is losing electrons. That's it. One line for each. Now let's move to the last or the first question. So there's a sample that contains 3 different types of atoms, statefully in terms of the number of subatomic particles. What these 3 atoms have in common? So that is the number of nucleons, right? Not the number of nucleons. They have the same number of. No, sorry, they have the same number of nucleons. They all have. So they all have 40. So proton plus neutrons are the same. I think they all have different number of protons and different number of neutrons, but the sum of the protons and neutrons is the same. Statefully in terms of the number of subatomic, how these 3 atoms differ from each other. So how do they differ? That's I mean they have different number of protons and different number of neutrons and also electrons as well. All 3 are actually different. A sample of sulfur contains only 2 isotopes. The relative atomic mass of the sample is 32.01. Calculate the percentage of abundance of these isotopes. So how do you calculate the average atomic mass? That's AR is the fractional percentage into the isotopic mass. And you keep summing this up. So what do you have the percentage? You don't know what the percentage is. So let's say there is X% of sulfur, that is 32. The other one would be then 100 minus X%. And that sulfur is going to be 34. So if this is 40%, this would be 60%. If this is 10%, this would be 90%. So if this is X%, this would be 100 minus X%. So all you have to do now is you have to put it in the formula. You already know what the AR is. That's given. So that is given as 32.09. So it's X% over 100 into what 32 plus it's 100 minus X% over 100 into the other one, which is 34. So you just need to solve this. I'll just multiply everything by 100. So this is, I think 3209 is equal to 32x plus 3400, I think, and minus 34x. If I solve this further, what is 3209? I mean, try and solve this. What do you get for x? Kisi ne kiya?
95.5.
Okay, so x comes out to be the 32 one. That comes out to be 95.5%. So what is the remaining one? What is 100 minus x? That's going to be 4.5. Okay, that's going to give you 4.5. फिर which orbital in sulfur atom has the lowest energy? So that is obviously the first shell one, that's 1s. Sketch the shape of a p orbital. So what is a p orbital? The electron density exists on either side of the nucleus. That is what a p orbital looks like. During the process of ionization of sulfur atom loses electron, identify the orbital from which this electron is removed. Explain your answers. So it is obviously the outermost 3p, and he's talking about the orbital. So it is being removed from a 3p orbital, 3px to be specific, but let's just call it a p orbital, a third 3p orbital. And the explanation is that it's furthest from the nucleus. Why is the electron always removed from the outermost? Because it's the furthest away from the nucleus, and it is the least attracted to the nucleus. So it is like really far away. Complete a diagram to show the arrangement of electrons within the third shell of a phosphorus atom. So phosphorus is 3s2 and 3p3. So s2 means they're both paired. 3p3 means each orbital in the 3p subshell will have one electron. And this is a typical question. Why is the ionization energy of sulfur less than that of phosphorus? So there are 2 marks. What is the difference between phosphorus's electronic configuration and sulfur's electronic configuration?
Sulfur has complete p orbital, therefore
Okay.
electron.
So first thing you're going to quote is that sulfur is going to have 3s2 and 3p4. Basically, you're going to talk about sulfur having a paired p orbital while phosphorus has unpaired p orbitals. And since it's got paired p orbitals, there's going to be repulsion. In the case of sulfur, the electrons, one of the orbital has 2 electrons. So there's going to be spin pair repulsion. So it becomes easier to remove electrons from the sulfur atom. Okay, that's about it. So we're done with this paper. So let's so this one is done. I think yep. So we're done with this paper. So let's continue tomorrow then. Okay. And does anyone have, if anyone has any questions, okay.